to another edition of Physics Videos. In this video we'll be introducing you to vectors. Vectors are measured or calculated values that have a specific direction. Previously we've been using a lot of values that we would call scalars. Scalars are measured or calculated values that don't have a specific direction. So let's talk about the difference in a measurement that you might see or make between a vector and a scalar. If you make a measurement of, say, distance, as a scalar that could be something like 18 feet or 49 miles or 0.38 meters. But as a vector, instead of displacement, that quantity would be called, instead of distance, it would be called a displacement. And displacements not only have a distance, but also a direction. It's a measurement from one spot to another. So 82 feet, 35 degrees west of north, or 1.1 meters, 18 degrees up from horizontal, gives a person directions from one spot to another spot. Now, a scalar quantity of speed might be 35 miles per hour, 9,500 meters per second, or 68 feet per second. Again, no particular way to go here. Now, if that speed has a direction, it's then called a velocity. Velocities have that additional direction, so not just 35 miles an hour, but 35 miles an hour, 61 degrees south of east, or 68 meters per second, 120 degrees left from some previous direction. Now, there is no special word for acceleration if it's a scalar, but you can still tell when an acceleration is a scalar or a vector by looking for the direction. An acceleration of 8.7 miles per hour per second, or 23 meters per second, or 68 feet per second is a scalar. It's not telling you which way this object is going, or which way this object is changing its speed. But 16 miles per hour per second, 15 degrees north of east, is telling you which way that object is being pushed or pulled, and how quickly it will change its speed as a result. So it's the issue of direction that separates a scalar from a vector quantity. Now, how do we use scalars? If we don't have a direction, we just assume everything is in the same direction. So a man walks 3.5 meters, then walks an additional 2.1 meters. How far has he walked? Well, we'd simply use algebra. We know that the total distance walked would just be the first distance plus the second distance. So 3.5 meters plus 2.1 meters means he's walked 5.6 meters. Now that's useful if we're trying to see something about his walking, but that's not as useful if we're actually trying to find him. If we don't know which direction he walked each of these 3.5 meters and then 2.1 meters, we don't really know where he is. Let me give you an example. Let's say it's the same man, but what he actually did was he lost his contact on the ground, so he's wandering the hallway looking for it. If he walks 3.5 meters and then turns 63 degrees left, then walks the next 2.1 meters, how far is he from where he started? We need a different system to find the answer. We'd actually have to draw out the answer. So first we'd have to figure out a scale. Now when we figure out a scale, we're just trying to make sure that we can draw 3.5 meters or 2.1 meters on our paper and not have it go off. A scale of 1 meter to 2 centimeters would work here. And then we simply draw out each vector. So if he walks 3.5 meters and then turns 63 degrees left from the direction he was going, and then walks an additional 2.1 meters, then he's really moved 4.8 meters from where he started, which 22 degrees left of the original direction he was traveling when he walked 3.5 meters. That would look like a solution to a vector problem. Of course, we should know how to do that, so let's discuss how you do it. In picking the scale, like I said, it's simply a matter of picking a scale that will allow what you're drawing to fit on your page in a reasonable way. But once you've chosen that scale, the 3.5 meters, if 2 centimeters represents 1 meter in real life, that would mean that 7 centimeters represent the 3.5 meters in real life. So you simply use a ruler to make sure that the arrow you're drawing is in fact 7 centimeters long so that it represents the real distance. Now, if the man turns 63 degrees from the direction he was originally traveling, to figure that out, you're simply going to need to bring in a protractor and measure, and you can see right here that that's where he needs to go to. Now, you just draw in the next vector towards that direction. And of course you could measure it with the ruler in the very same way. Now, to figure out finally how far he's gone, you're simply going to measure from where he started to where he ended, and you'd bring in the ruler again. To measure that distance. In this case, you can see that it's a little bit longer than 9.5. Whoop. And with that measurement, you could just divide it in half, 2 centimeters per meter, to find the distance he's traveled. Now, since the question describes the direction, the answer would also, and so you'd have to bring the protractor in again to measure the difference between the way he started going and the way he ended up going. Here you can see it's about 22 degrees. So the actual answer, the actual answer would be 4.8 meters, 22 degrees left from his original direction. Let's take a look at another vector problem. Here's one that involves acceleration. An impressionable freshman football player agrees to allow 2 juniors to strap 2 rockets to him. When lit, each rocket causes an acceleration of 67 meters per second. One rocket pushes the freshman south, the other pushes the freshman 19 degrees south of east. What's the resulting acceleration of the freshman? Well, clearly he's not going to rip in half and have 2 different accelerations. He's going to have one acceleration. But we can't simply do 67 plus 67 because the rockets aren't pushing in the same direction. So in order to solve this problem, we'll need to pick a scale. In this case, 10 meters per second equals 1 centimeter would make sense, so that the 67 meters per second would be drawn as 6.7 centimeters on our page. You can see when we bring in the ruler here, that length. Now, this vector represents the 67 meters per second south. To get the other direction, the other acceleration that is south of east, we would need to orient our protractor so that 0 points east from here. You can see that right now 0 is pointing east. And then we could measure out the 19 degrees here and draw the direction of the other vector. That vector would have to come out somewhere here. Now once we've done that, we can take the protractor away. We'd be able to bring in our ruler, align it with that mark, and then we could draw in the other vector. Now once that vector is drawn in, of course the ruler could go away, and we could draw a vector starting here and ending here, from the tail of the first to the tip of the last. And when we draw that vector, we could bring the ruler back in and measure its length. We find it's 11 centimeters long, which would represent 110 meters per second. Now, in order to fully complete the answer, we'd need to measure the angle. So again, we'd bring the protractor in, and we measure the angle. Now, if we point 0 this way, you can see that 0 is pointing towards the south here. So when we measure this angle, we're measuring an angle that is east of south. Now that angle happens to be about 35 degrees. So the correct answer to this problem would be that the young freshman will accelerate at a rate of 110 meters per second, 35 degrees east of south. That answer there represents the net effect of both rockets since they're acting simultaneously. I hope you've enjoyed the introduction to vectors. We'll do some more vector problems in class for practice. Thanks for watching, and we'll see you soon.